What do you get if you take a piece of glass and rule parallel, evenly spaced grooves onto it? Well, you get something called a diffraction grating. And today's video is going to talk about these weird and wonderful little devices. They come in various varieties with lots of different numbers of lines per millimeter, and understanding them can help us to explain why a CD does this, how to make groovy, hard to forge money, and how to produce fancy holographic wrapping paper. So let's get started. We can imagine that the glass consists of opaque sections and transparent sections. The opaque sections will obviously block light, the transparent sections will let light through. And if you understand the behaviour of basic diffraction, then if we send plane wave fronts up to this, and those wave fronts head in towards the gaps, then we would expect to see that light come out in the form of concentric circles, something like this. But we should realize that that is going to happen for each one of these little gaps, and so we'll get light coming out of all of them in little concentric circles like this. Now, as this light comes out from here, it will produce wave fronts, and you can see that all these waves are in phase with each other, all these are in phase with each other, all these are in phase. So we will get a set of waves heading straight forward. But we're interested in this particular video in what happens out at particular angles when we start to look out to one side. What happens then? And there are certain things that are true at very particular angles. So this is the diagram for waves heading straight out to the front, and you can see that they all have a constant phase relationship, and so a wave front heads across through all of these, and we'll get constructive interference directly in front of the grating. So what I've done here is I have put some lines in position in line with the start of each cycle. So you've got a full cycle in between these lines. They're all one wavelength apart. And I want to have a look at what happens when we start to move to different angles here. So the light's coming out from each one of these slits in all directions. But what I'm doing here is I'm just scanning this one round, and what we're interested in is what happens when it reaches particular angles. In particular, I want you to have a look here, and we're interested in when this slit becomes one whole wavelength ahead of this other slit, and you can see that'll be when this line arrives in here. So as the angle changes, we reach a point at this angle where the second slit is one wavelength behind the first. And that looks like this. At this point, every slit is one wavelength behind the one below it. So we start to get again a wavefront of constructive interference when we reach this angle. Now, if we were to keep going, we would eventually find an angle where the next slit is two wavelengths behind the one below it. And you can see we're approaching that now. When this arrives here, just about now, we've reached the point where it's two wavelengths behind. And that brings us to this point. And again, at this angle, we would find a wavefront travelling along out this way, giving us constructive interference at this particular angle. So we get this position where the lower or the upper sort of slit is one wavelength behind, then the upper slit is two wavelengths behind, then the upper slit is three wavelengths behind, and you can see due to the geometry of this system we can't actually get a 4 wavelength behind example, and so we would only expect to get constructive interference in this direction, in this direction, in this direction, and nothing else. So this is the 3 wavelength behind example, where we will have wave fronts traveling out together. So wave fronts that will be all in phase light heading this way. We should get constructive interference in that direction. And this picture is a static representation of the exact same thing. You can see that the waves that all come out at the same time will form a wavefront heading straight ahead. That's called the zeroth order. Zeroth. But there are also some other angles here. There's an angle in particular where everything is 1 wavelength behind, and this is in the downward direction now. There's obviously another position where everything is 2 wavelengths behind, and there is another wavefront where everything is 3 wavelengths behind. And so this is what we were demonstrating in the other direction. So we get what we call a first order corresponding to the red wavefront. We get a second order corresponding to the blue coloured in wavefront, and we get a third order corresponding to the purple. And so we would expect to see only constructive interference in these particular directions. So if we illuminate a diffraction grating with white light, we would expect to see this. So what's happening here? Well, the straight through, irrespective of what colour, what wavelength of light, will always be in phase. So you get a single white line here at the 0th order. As you go up through the orders, we get rainbow effects of increasing spread, and that's basically each wavelength, each colour will produce its own diffraction order. So blue will be a short wavelength, so it'll happen at a lower angle. Red being a longer wavelength, it'll take you to swing it out to a bigger angle before they go back to constructive interference, before they all end up 1 wave behind each other. And as you get to the higher orders, the spread becomes even more pronounced. So that's what you would get for white light, and you can see that these are a mirror image on opposite sides, because it's red is the furthest out in both cases, and blue is the closest in both cases, or violet is the closest in. If you were to repeat this with green light, which we could do, we could swap this for green light, we would expect to see something like this. So now we only have 1 colour, so we only get 1 very specific place where constructive interference occurs. So why do we get nothing in the in-between places? Why do we only get constructive interference at these particular locations? So if you imagine this is a place where all of the waves are arriving in phase, with each one being 1 wave behind the slit next to it. They're all arriving at some location. When you start to go to different angles, these amounts start to vary, and you start to get each wave arriving at a completely different position in its phase. And it's only when they lock back in to this particular case that we get them all being in perfect phase with each other again. And so because they're at various phases, we will have a downward displacement for every upward displacement, and so they all cancel, and that produces destructive at everywhere except for these special cases where they come in like this. So what about all these different coloured systems then? Well, if you think first of all about the CD is similar to the diffraction grating. The tracks on the CD are marked on it very, very close to each other, so it produces a version of a diffraction grating the reflected light is coming off the little surfaces in between where the tracks are drawn, and so it produces wavelets coming back from the CD that would produce interference. But what will happen is that white light consists of various different wavelengths, with red being very long wavelengths and violet being very short wavelengths. So each colour will produce constructive interference at a slightly different angle, and so it causes the light to spread out depending on where your eye is in relation to these surfaces. One part of this CD might be making yellow constructive interference, but from this position another part of the CD might be making red constructive, and you can see various other parts making blue and maybe even green. So the constructive interference happens at different places, and that actually means that a diffraction grating is useful for splitting white light up into the colours without the expense of a glass prism. Now, if you can control the actual lines themselves and vary their distance apart, you can start to draw coloured patterns, and that's what's going on here, where the lines have been changed at various points in the picture in order to produce various colours through this sort of hologram on a banknote. The same thing here, by messing around with the positions, angles and distances of the lines, you can start to etch in little patterns that produce all these amazing effects on the wrapping paper. So this also relates to, you can extend this behavior to producing things like holograms, and diffraction gratings are the basics of learning how to take your work with light much further. Okay, thanks for watching.